All right, you guys, we're going to talk about 10.2 through 3 today, which is arc measures and properties of chords. I know there were some problems on your homework last night that had chords on it, and we hadn't really discussed that, but real quick, let's go ahead and go to the definition of it. We're on page 133, and close to the bottom, we have this definition right here. A chord of a circle is a segment with two endpoints on the circle. And the fact that it has two endpoints on the circle means it's also considered a secant line. And the difference between a chord and a secant line is that the secant is actually a line that extends out of the circle, whereas the chord stops at the endpoints on the circle. So a chord is just considered part of a secant line. What is the largest chord in any circle? Well, that's going to be going across the widest part of the circle, which is called the diameter. Okay, so hopefully that will answer some questions that y'all had about last night's homework. I know that those first few problems were addressing the difference between secant line and a chord, and all of those things. All right, let's go back to the top of the notes. The measure of an arc formed by two adjacent arcs is the sum of the two arcs. We've already talked about major and minor arcs. Major just means that it's going to be greater than 180 degrees. It takes up a major part of the circle, in other words. Minor means it's going to go less than 180 degrees. And essentially we've talked about that the arc of a circle is just two endpoints and all points between. So we're following along the rim of the circle. That's going to be considered an arc. Any arc could be labeled with either 2 or 3 capital letters. Minor arcs are just with 2 capital letters. Major arcs, if you just have 2 points, you can't tell which direction around the circle you're going. So you want to make sure you have 3 capital letters, that middle point being a point of direction. So those are some examples of what you might see for a labeling of arc. So here we have a minor arc. Let's label this. Let's label this A. At the diameter, we'll label that C and B. Let me switch markers here. Okay, a minor arc could be considered from A to C. You could also call A to B or AB an arc that is minor. A major arc, let's label the same way. We'll put A here, C there, and B there. A major arc would start at A, head towards B, and end on C. So we'll go around the circle towards B and end on C. Do you see how that takes up the majority of a circle? That would be considered a major arc. A semicircle just goes from one part of the diameter all the way across to the other side. So we still have points C, A, and B labeled. We could have semicircle C, A, B, or you could have semicircle if you had another point down here. Let's say we call this point D. You could have arc or semicircle C, D, B. So under semicircle, let's put that this is equal to 180 degrees. And it needs 3 points as well, because again, you don't know if you're talking about the top half or the bottom half of the circle. All right, so look at our circle in this next picture. We need to label all of the minor arcs, 3 major arcs, and 2 semicircles. Now on the ones that specify how many I want, there's a bunch of different options, so you could come up with a bunch of different answers. Let's start off by naming all of the minor arcs. I'm going to start at A, so I have AB. So I'm going to write AB with an arc above it. I have A to C, because that's still less than 180 degrees. And A to D would be my next guess, but again, that looks like a semicircle, so I wouldn't put that as a minor arc. So now I'm going to move over to B. I have BC. I have B to D. And I could also do B to E, because that's still not quite 180 degrees. Now I'm going to start from C. I'm going to continue going around the circle until I have them all listed. So I'd have C to D, arc CD, arc CE, and arc CF is a semicircle, so I move on. Now I have DE, I have DF, no more from D, so then I go to E. You could do EF and EA. And the last arc is going to be from F to A. Let me count and make sure I have all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're missing one. What's the last one? Do we have FB on there? No. FB is going to be the last one. I went from FA to FB. All right, so you should have 13 total. Now we need 3 major arcs. You can pick any major arcs. Major arcs are labeled with 3 points, so I put FAD. You have the starting point, the point that leads direction, and then the end point. I could also do ABE. And I could also do FDB. Again, there's a bunch of answers you could get on this. All right, now we need to name 2 semicircles. Well, you have 2 options actually. If you look at diameter FC, you could have this semicircle on top, or you could have the semicircle below FC. You could also do it in relation to AD. And I chose mine from AD, so I'm going to do the left semicircle as ASD. I could have also chosen AED because that still leads that same direction. And the right semicircle I'm going to call ABD. All right. Using that same semicircle, let's determine what the missing values are. If the measure of EF is 80 degrees, and the measure of CD is 68 degrees, and the measure of BC is 52 degrees, I can find every other missing arc from here on out. So the measure of DE is right next door to both of the angles, or the measures of the arcs that they gave me. Well, what I notice is that all 3 of those arcs together form a semicircle, which is exactly 180 degrees according to our notes. So I'm going to say, okay, well, what's 180 minus this 80 degrees minus 68 degrees? And that's where I'm going to get 32 degrees for arc DE. Now I'm going to use that same concept for AB. AB is right next door to arc BC and CD, and I notice that all 3 of those arcs add up to 180 degrees, which is a semicircle. So I'm going to take these 2 measures and subtract those from 180. So I want 180 minus 68 minus 52, and you get the value 60 degrees. So I'll label my picture as I've come across these things. Next, they ask for the measure of ACE. A semicircle plus this arc right here. So I'm going to take 180 degrees and I'm going to add 32 to that, which is where I'm getting 212 degrees. So that was 180, a semicircle, plus 32 degrees. Now it's asking for A to E to D. Well, that's exactly a semicircle, so that should be 180 degrees. The next one, D, B, F. I'm missing this portion. We have a semicircle plus the measure of FA. Okay, how could I find that? Well, this is part of a semicircle with part of semicircle FAC. So if again I take 180 and I subtract out the two measures I know, the 60 degrees and the 52 degrees, then I'm going to get that this piece right here is 68 degrees. I could have also noticed that line segments AD and FC intersect to form an X. Technically, these angles right here are vertical angles, so they would be congruent. If the interior angle is going to be congruent, you know that the arc that's formed by it has to also be congruent. So you could have also looked over here and said, okay, 68 degrees is going to be equal to 68 degrees. So now to find DBF, we would add all those values together to get 248 degrees. So we would go 180 plus 68 is 248. The last angle, EAB, goes to clockwise actually. So we have 80 plus 68 plus 60, which is giving me 208 degrees. Find an arc that measures 280 degrees. I'm just going to randomly select some angle measures that are next door to each other that are going to add up to 280. And I noticed that from F towards B, so 68 plus 60 plus 52 plus 68 plus 32 ended up giving me 280 degrees. So I would call that arc FBE. I knew it had to be a major arc because it's definitely more than 180 degrees. All right, let's go on to the next page. We did not answer that top question. Is a radius considered a chord? Well, a radius goes from the center of the circle out to an endpoint. So therefore, a radius only has one endpoint, so it would not be considered a chord. It would need to intersect twice. It needs two endpoints on the circle. All right, our first theorem for today says if we have in the same circle or congruent circles that are next door to each other, if we have two minor arcs that are congruent, then it must be because their chords or the corresponding chords are also congruent. So for example, each of those chords is 10 and they're forming or connecting the arcs that are both x degrees. That means that all of those are going to be the same. So if I knew this x was 30 degrees, I automatically know the measure of this arc is 30 degrees. Here, same thing, we have chords that are congruent. I can automatically conclude that the measures of these angles are congruent, or measures of the arcs. And vice versa, the measures of the arcs are congruent, so I can say that the chords are also going to be congruent. All right, our next theorem, if we have one chord that is a perpendicular bisector of another chord, in other words, it's meeting at a 90-degree angle, and it's cutting one of those chords in half, then the first chord has to either be a diameter or a radius, depending on where that chord stops. So if it stops in the center, it's going to be a radius. If it stops on the other end, it's going to be a diameter. Theorem 10.5 just discusses being perpendicular to a chord. If a diameter or radius is perpendicular to a chord, then it must bisect the chord and the arc. So I can automatically conclude that this piece is congruent to this piece. Oh, y'all can't see that, sorry. The 5 is congruent to the 5, and I can conclude that the arc from the chord to the radius and radius to the other side of the chord, those are going to be both congruent. All right, so let's look at some examples of this real quick. Okay. Oh, we have one more theorem. All right, theorem 10.6. In the same circle or congruent circles, congruent chords are perpendicular. This would be equidistant. Equidistant means equal distances. We've discussed this before. So that means the point on my chord that is perpendicular to the chord, as soon as I intersect with the center, those are going to be the distances that are the same. So from the center to the angle, center to the angle, those are going to be congruent. All right, so let's put some of these into motion. For number 1, all I know is that the diameter is 20 inches. So from the top of the circle to the bottom of the circle is 20 inches. What I notice about this chord right here in the center is that it is a diameter. So if the diameter is 20 inches, I can break this up into 2 congruent pieces to say that each of those is 10. I have this chord over here that I know is broken into 2 congruent pieces. One of my theorems says if I have 2 congruent pieces, it's also perpendicular, which happens to be labeled for us. And if you look at this top piece, we have a top right triangle, where 2 of my sides are known, 1 is unknown, and no other angles are given, which means you cannot use special rights, you cannot use SOHCAHTOA. We have enough information to do Pythagorean theorem. So x squared is going to be equal to the hypotenuse squared minus the other leg I know squared. So when I solve that, I end up getting x squared is equal to 36, and therefore x is going to be 6 inches. Now don't always go by the picture. This looks a lot smaller to me in relation to the other sides than 6 inches, but the math told me it's 6 inches, so don't go by looks on your pictures. All right, number 2, we're given a diameter of 20 again, so I'm going to go ahead and directly label my chord that is the diameter to say that each of those is 10. And what happens that you notice is that from here, the center of the circle to the edge is 10. So I can go ahead and automatically label every radius that I see in this problem. So I notice that that is a radius. This piece right here is also a radius. So I'm going to go ahead and label them as so. And I already have 2 right triangles that I could pick information from to use Pythagorean theorem. So we'll do that again. X squared is going to be equal to the hypotenuse squared, 10 squared, minus the other leg squared. We end up getting x squared is equal to 75. This is not going to come out perfect, so you're going to have to simplify your radical. 75 I can split into factors of 3 and 25. I know the square root of 25 is 5, so I'm going to take that square root, and the only number I have left in my square root is 3, so this is going to be 5 square roots of 3 inches. All right, number 3. X in this picture is representing the whole length of the chord, so you may want to break this up, either name half of the chord a different variable, or assign this variable to a different piece. Like, for example, you could call, okay, this is x, and know that you want to find the whole chord. I strongly suggest picking a totally different variable to represent from the side of the circle to where your 90-degree angle is, so there's little confusion. All right, so Pythagorean theorem again. We have y squared equals the hypotenuse squared minus 4 squared. We end up getting y squared equals 20. So again, we're going to have to reduce your radical. The square root of 20 can be broken into 4 and 5. I know the square root of 4 is 2, so I pull it out. 5 is a prime number. It's left under my square root. Now I have to think back. Okay, I didn't want just a piece of that chord. I wanted the whole thing. So you're going to have to use the theorem that says if this chord is perpendicular to the center of the circle, then those pieces must be congruent. So I'm going to double this times 2, and we end up getting 4 square root of 5 units, because again, I don't have units on this one. Number 4 is pretty quick, and there's actually very little work for those of you who hate showing your work. Okay, so right now we have that these two chords are equidistant from the center of the circle. And I know that because both of their lengths are 5. So that tells me, according to the theorem that we just discussed at the top of this page, if they're equidistant, then the chords must be congruent. So I'm going to go back to my problem. If they're all going to be congruent, well, this entire chord is 14, so therefore that entire chord must also be 14 units. All right, number 5. Number 5 says to find x and y. Y is representing the diameter of the circle, which is why it's drawn out here. If I was to put a y in the problem, it kind of is confusing about which piece of that chord you're talking about. So y is going to be the entire diameter. We'll probably need to find that one a little bit later because we need some information in here first. The first thing that I would notice is that this line right here, this diameter, is perpendicular to my chord. So I can automatically say that these two pieces must be congruent. That diameter is perpendicularly bisecting that angle. So I can say x is going to be equal to 5 square root of 3 units. That one was pretty quick. But I still need more information to find y. I need to find this piece right here, this piece right here, and this bottom piece right here. All right, so there's an error on this problem. The first thing that you should know is that this is supposed to be labeled 5. And this is also supposed to be labeled 10. And I did not make up those values. They should have been written in the problem. So the only part of y we need to find is from the center of the circle to where the chord intersects. And this is forming a right angle and also a right triangle. And not just any right triangle, it's forming a 30, 60, 90 triangle. So let me get a different pen here. Across from the 30 is always a value of 1. Across from the 60 is always a square root of 3. And across from the 90 is always 2. We really don't care about finding that side because it doesn't have anything to do with y. So we really don't even have to go that far. The first thing you want to start on, though, is the side we actually know information about. So we're going to divide 5 square roots of 3 by the square root of 3. And what happens is those square roots cancel to give you 5, and then we'll multiply to get out. 5 times 1 tells me that this side is 5, and I could have gone further to see that this side is 10, but again, you don't really care about knowing that information. So now to find the diameter all the way across, I just add these up. 5 plus 5 plus 10 tells me that y is going to be 20 units. Okay, number 6 is a little bit more complicated. You have to notice some things that are going to be congruent to each other. The fact that this chord is perpendicular to the center of the circle tells me that these pieces are congruent. So if the whole side, AB, is 30, then each piece is 15. And I broke it into that because that's what's going to get me to my individual right triangles. The second thing you can notice is that the fact that these two are going to be congruent, and this piece right here, we'll just call that C for the center of the circle. AC is considered a radius. So I'm going to go ahead and label any other radius in the problem as 17 because they should be congruent. So same thing over here. Now what I have is an isosceles triangle where this line that is perpendicularly bisecting the bottom side tells me it's also bisecting this angle at the top. So if that right side is 62 degrees, x must also be 62 degrees. So I'll write x equals 62 degrees off to the side. Now the last little piece is to find y. Y is representing the height or the length of the altitude of this triangle. I can do Pythagorean theorem where y squared is equal to the hypotenuse squared minus 15 squared. We end up getting y squared equals 64, so y is a value of 8 units. Because again, we do not have labels here. All right, number 4. Kind of spread out information, right? We don't have enough information in this one triangle, but we do have information to get us to that right triangle so that we can use Pythagorean theorem. First things first, this chord is perpendicular to the center, so everything on the left should match the right, which tells me this piece is also 4. This piece right here, this segment, goes from the edge of the circle to the center of the circle. That is considered a radius. So I'm going to go ahead and label all the other radius in the problem as x, which happens to be the third side of that triangle. So now I have enough information to do Pythagorean theorem to solve for that x value. So 3 squared plus 4 squared equals x squared. When you simplify that, you get 25 equals x squared. So x must be 5 units. All right, that pretty much sums it up for notes over 10.2 through 3. For the rest of class, I want y'all to do homework number 27, which is bookwork. There's no worksheet for this unit. Keep the homework from last night. Consider it your lucky day if you forgot to do it. I will collect those tomorrow on Friday for a grade, and that way I can answer any questions you'll have over the homework before your quiz on Friday. So we are taking a quiz on Friday over 10.1 through 3. Okay, so homework 27 and homework number 26 are going to be due on Friday. Homework 26 should already be done, so that shouldn't be any work for y'all. I'm trying to think of any other announcements that I have for y'all. That's pretty much it. I'll be back tomorrow. If you have any questions on homework, star them, circle them so you know what to ask me about when we come back so that y'all can be prepared for the quiz on Friday. All right, y'all have fun and please be good. I'll miss y'all. Bye.